All right, welcome to the next lesson in the dynamic balancing course. In the first lesson, we talked about some of the definitions of balancing, and we looked at a few of the causes of imbalance. Now, given the fact that those types of imbalance are present, the way in which the weight is distributed around the shaft axis is a it basically we need to classify the types of imbalance now. So we looked at the causes. Now we have to figure out, like, when we have a cause, what type of imbalance is it. We need to know that before we actually set out to start making corrections to the unbalance of a rotating piece. So when balancing a rotor, such as a fan or a motor, the objective, of course, is to reduce the imbalance forces and vibration at both support bearings of the rotor. Whether or not this can be accomplished by making balance corrections in one plane or location along the rotor depends on the type of imbalance that exists. With some types of unbalance, it will be necessary to make balance corrections in two reference planes along the length of the rotor. Therefore, it is important to recognize the type of rotor imbalance before we start that balancing procedure. Knowing the type of imbalance will determine the balancing technique required, single plane or two plane. So imbalance was defined earlier as simply an unequal distribution of weight of a rotor around its rotating center line. However, unbalance can also be defined as a condition where the rotating center line and center principal axis do not coincide. Okay, so that's a little bit wordy there, but I'm just going to kind of show a few pictures that will explain it. And the best way that I can do that is to if I have two pencils here, this would be the rotating center line, or the center axis of this would represent that. There's a rotating center line of the shaft axis. Okay, but then if I took that same weight distribution and I actually looked at it, I'm going to have a actual central principal axis, and that's not going to coincide. They're going to look slightly different. So how that central principal axis and how that rotating center line actually relate to each other is going to determine the type of imbalance that we have. So the rotating center line, or my shaft axis, is the actual measured. Okay, like if I took the shaft and I measured, it's the kind of physical center. It's held in position by bearings, and it's locked and it's located in that position. The central principal axis is a little bit different because this is the actual weight distribution. And I kind of joked, and we talked about in space. If you were to take an object, any object, up into outer space where there's no gravity, and then you spun it, it's not going to spin around the measured center point that it's located. It's going to rotate around the principal axis, or the weight distributed because of the centrifugal motion. And that's really at the heart of what we're looking at today. So when we talk about the shaft axis, that's the actual center line of the drawing of the shaft. And that is fixed and held by bearings, and that's what everything rotates around. But the central principal axis is how the weight is distributed among the rotor, and what it wants to do and how it's located. So if we took it up into space and we spun it, it's going to find a home and it's going to spin, and then we can just kind of like grab it and pin it at that point, and it's just going to rotate around that. So the idea of balancing is trying to take that principal axis and the shaft axis and make them coincide, or make them the same. And so that's what we're gonna look at. So the first type of imbalance that we have here is static. And static imbalance is an imbalance condition where the central principal axis is displaced but parallel to the shaft axis. So in the picture here, in the diagram, you can see that the shaft axis and the principal axis are in line. So they're in line, but they're just slightly out, like they're parallel to each other. There's no angle there. It's just displaced. So that's what static imbalance is. This type of balance is also called force unbalance. So static unbalance can be pictured as simply one heavy spot located in the center of the rotor, which simply acts to displace the center of gravity of the rotor away from the rotating center line. So static imbalance can be detected by simply placing the rotor on knife edges or rollers, and then allowing the heavy spot to just kind of swing to the bottom. However, if the rotor is spinning, static imbalance is easily identified because the vibration amplitude at the bearings is going to be for both bearings are going to be in phase, meaning that as the rotor is spinning, the bearings and how it's held is going they're going to have, instead of it being like, the displacement being the the load on the bearings being out of phase, it's going to be in phase. So that both that wobble is going to be equal on both bearings. Okay, so in other words, well, yeah. So it would be possible to reduce the imbalanced vibration at both of those bearings with a single correction weight located at the middle of the rotor. Or if the center plane of the rotor was not accessible, the balance correction would simply be divided or split between the main edges of the plane at the same angular location. So we can kind of visualize this. I have a little kind of teaching aid here. Okay, and what this is two planes. We have a plane on this side, a plane on this side, and then I have a shaft in the center that I can hold either with one hand or with two hands. It helps for showing just when I hold it with two hands. So as I spin this around, you'll see that these weights that are on this part fall to the bottom. Okay, so now they're at the bottom. That is a static unbalance. And as I spin this around, I can feel equally, if I was to hold this at both ends, I can feel the same rotating force as it wants to spin around. Okay? Need some oil. But the main point that I'm trying to get at is that because this is my shaft axis, but my principal axis is closer to where this weight distribution is, somewhere around here, right? That when I spin this around, it wants to come towards you, and then it comes up and then towards me and then down. So depending on how it's spinning, those bearings are going to both equally have that weight distribution loaded and applied to it all the way around. Okay, so I'll give one more spin just to show. And then it nicely falls and sits down at the bottom and lands. And that is static unbalance. Okay, so static unbalance is central principal axis and shaft axis parallel to each other. The load is in phase. The next type of imbalance that we have is called couple imbalance. Couple imbalance is a condition where the central principal axis intersects the shaft axis at the rotor center of gravity. A couple imbalance can be represented by equal heavy spots located at each end of the rotor, but directly opposite or 180 degrees opposite one another. Unlike static imbalance, couple imbalance cannot be detected by placing the rotor on parallel knife edges or rollers. Couple imbalance only becomes apparent when the rotor is spinning. The reason for that is it's offset and balanced so that it's not going to necessarily fall to one spot like a static imbalance will, But when it's running, we can feel the bearings go 180 degrees from each other as opposed to static when they're going forward and backwards at the same phase. Okay, and we'll talk about phase a little bit later. Okay, so however, like static imbalance, couple imbalance is easy to correct since it is obvious that balance corrections in either 180 directions opposite each other will be required to solve the problem. Although balance corrections are needed in two planes, since the relative amounts and relative angular locations are already known, a couple imbalance can actually be solved using a simple single plane solution. So static and couple can be corrected in one single plane. Now, I'll use my little demonstration here. This was what a static looked like. Okay, so it falls to I can detect it at the standing position or a stationary position. But if I take the weight now, okay, and I want to make sure it's nice and straight, now you can see that I have one weight here at the bottom, and then I have one weight here at the top. Okay, so when I spin this, I can feel it, but there's not necessarily one single spot it's going to fall to. It's not going to swing to that bottom at rest. But when I spin this, you can see that my hand kind of wobbles because I've got two weights evenly distributed out of, so it wants to do this. Or if I was to hold this in two locations like here and give it a spin, my hands are being pushed and pulled in two different directions like that. Okay, so this is what a couple imbalance looks like. The centerline axis travels through the center but down on an angle this way, and it will just land wherever it wants to land, and I can't detect it at station because it will just stay in any position. The next type of imbalance that we'll look at, this one isn't in your Alberta ILM, but I think it's important to discuss anyways. So in some cases, will rotor have a completely true static or a completely true couple imbalance? In most cases, an unbalanced rotor will have a combination of the both. So one special combination of static and couple imbalance is called quasi-static imbalance. And this is shown in the picture here. So what this looks like in the diagram is that we have a single heavy spot located at one end instead of the center, like a static imbalance. So this, excuse me, what we're looking at is that this, let's grab a different color. This weight on this side is much bigger than the weight at this side. So it's like looking at a couple imbalance. If I was to take this couple imbalance setup, and if I was to add more weight to one side of it, and what it's done is instead of taking the center line that runs directly through the center, now what it's doing is it's bringing it over slightly. So it will find a home, it will find a center where it's always going to land at the bottom. Okay, and here I can adjust it by doing this. Okay, so I've moved this weight a little bit closer to center. So when I spin it, I still get the wobble, and it's detectable at rest because there's more weight further distributed out that it wants to find that position. Okay, so it's a combination of static and couple. The last one that I want to look at is called dynamic imbalance. Dynamic imbalance is probably the most common type of imbalance condition, and it accounts for any condition that does not meet the conditions of a static, quasi couple, or quasi-static imbalance. Basically, a dynamic imbalance is a random combination of static and couple imbalance together. So we have the shaft axis are off parallel and they're off kind of angular. So we don't have that crossing of the central principal axis and the shaft axis. And it can best be illustrated with this tool again. So I will change the weights to be, slightly different positions here. Okay, so we'll go like here and here, let's say. And then what we're also going to do is we've been running this thing with this in like an H position, but now we're going to rotate it like this. Okay, and it's got a heavy spot and it definitely wants to wobble when I hold it. Okay, so you can see the wobble that goes on when I spin this. Okay, so that is a dynamic imbalance. It means that we have two planes. They are different amounts of imbalance on each side. They're at different angles to each other. And I could best describe this in terms of shaft alignment that you guys have done, where you have an offset alignment, but then you also have an angular misalignment. So yeah, basically those are the types of imbalance. We had static imbalance, which is when you have the same forward backwards motion on both bearings, equal amounts. And then we had couple imbalance where they're 180 degrees to each other and we can't detect it when it's stationary. Then we had quasi-static where the imbalance is 180 from each other but it's slightly different, and so we can be fooled by that because we'll think that it's a static imbalance but it's actually a little bit off for both. And then there's a dynamic imbalance where they're completely out of phase of each other and we have just a random wobble that's happening because our central principal axis and shaft axis are offset and angular and turned out of phase from each other. So those are the principal types of imbalance, and that's the lesson for this week. Make sure that you guys finish your assignment for this one, and I'll see you next week in the next lesson.